Thank you, Chandrasekhar, for the kind introduction, and to the QMAT organizers for inviting me to this wonderful event. Okay, so I'm going to show you that simple looking materials like these binaries can show anomalous and interesting properties. So this is what I plan to do, and hopefully time will permit me to cover everything that I've planned. If we look at the resistance of metals, for very good clean metals, we expect that the resistance goes linearly with temperature, at least at high temperatures. At low temperatures, of course, phonon T to the 5 block, etc. comes in. So, but at high temperatures, it should go linearly. Now, keep in mind that we are talking about very, very good metals. Look at the resistivity here. It's in micro ohm centimeters and only a few micro ohm centimeters. Okay. On the other hand, if you have disordered metals like alloys that we sometimes work with, then you will see almost universal behavior like this, where the T to the 5 from phonons rolls over to something which looks like a saturation. And what happens is that as the temperature is increased, the scattering rate increases, and when the mean free path becomes comparable to the lattice constant, then the resistance must saturate. And this maximum resistivity that a material can attain is called the Mott-Ioffe-Riegel limit. And most disordered materials will show this kind of saturation at high temperatures. But there are several classes of materials which have been found to show resistivities which show no saturation, even though the resistances are such that the mean free path can no longer be said to be larger than the lattice constants. Okay. So these are the heavy fermion superconductors close to quantum critical points. The cuprates, of course, we heard a beautiful talk about this yesterday. And even the iron arsenide superconductors close to the optimal doping. All of these show linear resistivity at high temperatures with very, very large values of this resistance, and therefore it is not clear whether a quasi-particle picture is even valid at these in these materials at high temperatures. And not just alloys like these, even fullerenes, doped fullerenes show linear resistivity at large temperatures. And look at the size here, milliohms. Okay. So, what is common to all these families of materials? So, just like the shortest length scale is the Planck length scale, one can phenomenologically introduce a scattering time, the Planck time, which is given by h bar by kBt. And what is its connection to resistivity of these materials? If you look at within the Drude theory, the conductivity goes as Ne squared tau by m, where tau is the scattering time. And one can evaluate from experiments the scattering time and relate it to Fermi surface parameters. And if you take the ratio of this scattering time found from experiments to the Planck scattering time, then you get a dimensionless ratio alpha called the Planckian ratio. And it turns out that in all these materials that I showed you and many more, even though their Fermi surface parameters are very, very different, so for example, the Fermi velocities differ by orders of magnitude, all of these materials show a Planckian ratio of 1. Okay. So this is the heavy fermion superconductors, the iron arsenides, the strontium ruthenate, which I didn't even show you. This is a nematic material, and the cuprate material. So all of these go as alpha equals to 1. Now the common thing about these materials is that they are strange metals, what are called strange metals. They are either close to magnetism or quantum critical points, Even twisted bilayer graphene shows this, and so on. So it seems that alpha equals to 1 linear temperature resistivity requires some kind of anomalous correlation effects, etc. So we will show that in our materials, none of these things are happening, and yet we get large linear slopes in resistivity. Okay. But let me first introduce the materials to you so that we appreciate that on the face of it, these seem to be very, very common boring metals. Okay, so this is the crystal structure. This is also an example of how science progresses non-linearly. When we started this in 2006, the motivation was to try to find another high temperature superconductor like MgB2. So MgB2, of course, has a famous boron honeycomb lattice. In these materials, we had, if you look down the c-axis, we have a boron honeycomb lattice, but it is warped in the third direction. And therefore, we were looking at some similarities with MgB2 and trying to see if we could get a superconductor. Okay. So this is the collection of normal state properties, the resistance as a function of temperature for both materials. We will come to the large linear slopes in a moment, but look at the inset where the low temperature resistivities are extremely small. So they are very, very clean metals. The susceptibility is temperature independent for most of the temperatures except at very small temperatures. And also note that the susceptibility is temperature independent and negative, which is surprising for a metal. And this just means that the core susceptibility, because osmium and ruthenium have a large number of electrons, the core susceptibility, which will give you a diamagnetic contribution, is much larger than the polyparamagnetic susceptibility. If you account for that, you get a positive polyparamagnetic susceptibility, which you can relate to density of states, etc. And here is the heat capacity. So you can look at the inset to see that the Sommerfeld coefficient is tiny. I mean, 2 millijoule and so on, like copper. So these are, by these diagnostics, these are very standard boring metals. So let us, well, we were also able to grow single crystals, and the point is that the crystals show properties which are very similar to the polycrystals, which just shows that the polycrystals themselves are very, very clean and well crystallized, etc. Okay, so this is band structure on osmium diboride and ruthenium diboride. This was done by Bahadur Singh's group at TIFR, and this was done by Sudeep Ghosh's group at IIT Kanpur. Spin orbit coupling has been included, and you can see that there is a continuous gap in the whole Brillouin zone, and this allows us to make a topological classification as we would for band insulators. Okay. So when this is done, we get a topological index of 0, 0, 1, 0. I'll talk about this if somebody wants. So these are Z2 metals, which means that their surfaces will have spin polarized topological surface states. Okay. So for example, you can see Dirac-like cones close to the Fermi energy coming from the surface states, the topological surface states. Okay. So the DFT also gives us the band structure, the Fermi surface, and the Fermi surface is made up of 3 sheets, 2 3-dimensional ellipsoidal sheets which are nested inside each other, and 1 tubular sheet which runs along the B axis. Sorry, these indices should be swapped. This is H parallel to B and this is H parallel to C. Now, so the Fermi surface can give us various parameters like the Fermi velocity, effective masses, and so on. And to compare with experiments, what one does is one can do quantum oscillation experiments, which we have done. So this is the change in the frequency of a tunnel diode oscillator, which roughly measures the skin depth, which roughly measures the conductivity. Right? So this is, you can see as a function of field, the conductivity has some power law behavior, and on top of those are nice oscillations. So if I remove the background, I am left with this oscillating signal, which I can Fourier transform to get out the frequencies. And if I track the amplitude of the frequency as a function of temperature, I can look at the effective masses coming from the various bands, etc. Okay.
Is Richard also explained?
Yes, yes, yes. So this is a busy slide, but it collects all the Fermi surface parameters that we could extract. So things that I will use later is the following. So there are two ellipsoids which are nested inside each other, and they contribute a certain density of states. And the anisotropic tubular sheet contributes the largest. Okay, so the most of the density of states comes from the tube. Okay. On the other hand, if you look at the effective masses, they are all weakly correlated, so close to the free electron mass. The electron phonon coupling is also small, which is consistent with their very low TCs, which we will see later. The Fermi velocities are also obtained, and you can see that the Fermi velocities of the ellipsoids are a factor of 2 compared to the tubular sheet. So the Fermi velocities of the the tube is the smallest, whereas the density of states of the tube is the largest. Okay. And the Fermi velocities of the ellipsoids are largest, although they contribute a very small fraction of the density of states. Okay, so we will use these later. I will come back to superconducting length scales, but the take home from this table is that both materials are very, very strongly type 1 from these calculations. Okay, so unconventional superconductivity. So already we've seen that these simple looking metals are topological Z2 metals. So the first surprise was that. The second surprise is that we have evidence of unconventional superconductivity in these materials. So this is a collection of superconducting properties at various magnetic fields. So this is the resistance at low temperatures as a function of field, and you can see that systematically the superconducting transition is suppressed. Look at the magnetization as a function of field. This is typical of type 1 superconductor, very V-like, and not the gradual increase of magnetization as a function of field that you would see in type 2 superconductors. The heat capacity as a function of temperature in 0 and applied field of 1 kilo oersted. The critical field turns out to be very, very small, as you expect for a type 1 superconductor. RuB2 has similar features. It looks very type 1 like again, and the specific heat and in fields shows that only a 250 oersted field is able to suppress the superconductivity completely. So these are very small Hc type 1 superconductors. We have evidence that these materials are multi-gap superconductors from the following observations. So if you look at the heat capacity jump at the superconducting transition, the BCS theory for a single gap superconductor gives you an estimate that the jump divided by the gamma Tc should be 1.43. Okay. So there is a slightly reduced value for OSB2 and an even smaller value for RuB2. Okay. For OSB2, we were able to do penetration depth measurements down to very low temperatures, and you can see that the data does not fit a single S-wave gap at all, and it can be fit with a 2-fluid model, and which is consistent with our heat capacity, giving evidence that these materials are multi-gap superconductors. In RuB2, we were not able to do a penetration depth measurement, but the heat capacity could be fit beautifully with a 2-gap fit, although the single gap fit does not fit it at all. Both at low temperatures, there are deviations, and at the Tc. Okay. So both materials appear to be type 1 multi-gap superconductors. So evidence for type 1 also comes from heat capacity in a field. So you look at the heat capacity at the superconducting transition in 0 field, and as soon as you apply a field, this second order transition becomes first order. So this is again consistent with the type 1 superconductor. So this happens over multiple crystals, and although RuB2 was measured on polycrystals, you can still see indications that the heat capacity jump in a field is larger. Okay. The magnetization curve for RuB2 is again very sharp and V-like, and therefore again both these taken together suggest that this is again a type 1 superconductor. So mu-SR measurements were done in collaboration with Ritu Gupta from IIT Ropar, and this is the relaxation, muon relaxation as a function of time at two different temperatures, one above the TC for OSB2, for RuB2, which is 2 Kelvin here, and one below TC. The TC for RuB2 is 1.6, remember? So this was done at 10 millikelvin, and you can see that there is a strong enhanced relaxation below the superconducting transition temperature. This suggests that there are internal magnetic fields inside the superconducting state which were not present in the normal state. So we can track the relaxation time as a function of temperature by doing similar measurements at various temperatures, and that has been plotted here, the relaxation rate as a function of temperature, and this has an order parameter like temperature dependence, which kicks in at TC and continues all the way down. Okay. So this is clear evidence that the superconducting state breaks time reversal symmetry. These are depolarization rates in a transverse field, and so this is roughly the penetration depth or the superfluid density. So a superfluid density can be fit to find out what the order parameter, superconducting order parameter is, and you see that both a single gap S wave as well as a multi-gap S wave fit the data equally nicely. But because we have multi-gap evidence from other thermodynamic measurements, 5 minutes left for 25, right? So the proposal is that this S plus S wave is the better fit to this data. Okay. So Shudip at IIT Kanpur has done some symmetry analysis based on the crystal structure, etc., and proposed that internally antisymmetric non-unitary triplet superconductivity is what is happening here. I can talk about this if anybody has a question later. Okay, let's come to the super Planckian transport. So this is the resistivity as a function of temperature again, and you see that they are very good clean metals. But at high temperatures, once the T to the 5 phonons go away, the high temperatures up to, well, we've been able to measure up to 385. We plan to measure at higher temperatures. It is completely linear. I mean, I wasn't able to show the derivatives, but the derivatives climb and then go flat. So it is really linear resistivity up to very high temperatures. So the linear slopes are these, and if I just use a single band model that I gave you before to calculate the Planckian ratio, I get a Planckian ratio which is an order of magnitude larger than even the cuprates and heavy fermions and so on. So this is very anomalous. Okay. However, we have seen that both RuB2 and OSB2 are multi-orbital metals with 3 Fermi sheets, and therefore one cannot use a simple single band expression, and maybe a better way to do it would be to do a multi-band analysis. So VF is the average VF we found from SDH oscillations.
For a particular sheet,
We took an average for the single band analysis, but here we will take the sheet resolved VF. So treating the system as a collection of parallel conduction channels, the total conductivity can be a sum of the conductivity of each channel. And therefore, if you have several sheets, this index is a sum over sheets, you can get a total conductivity from here using the Fermi surface parameters that we extracted earlier. So using this, we get the Planckian ratio to 3.2 for OSB2. So from 8 we have been able to bring it down to 3.2, but this is still larger than alpha equals to 1. So this is where we are currently. The other thing is that for RuB2 we don't have single crystals, and therefore we don't have Fermi surface parameters, but Sudeep has promised to calculate them and send them to me. At least we'll have them theoretically, and then we can use them for to see what RuB2 does, because RuB2 the single band was giving even larger alpha of 15. So therefore we still have to figure out where this large alpha is coming from. Electron phonon doesn't seem to be bringing it down to alpha equals to 1. Okay, so the conclusion is that RuB2 and OSB2 show large super Planckian, and by super Planckian I just mean that alpha is larger than 1. Super Planckian scattering rates, and a multi-band analysis somewhat reconciles this as coming from electron phonon, but we are still not satisfied, and we have to still worry about it. The band inversion, because of the strong spin-orbit coupling, leads to a Z2 metal characterization, and this leads to topological surface states at certain surfaces on the crystal. μSR reveals that inside the superconducting state, time reversal symmetry is broken. Therefore, some unconventional pairing must exist. And the superconductivity could also be type 1 and multi-gap. So therefore, even though these are simple looking metals, and if you just do the normal thermodynamic and transport measurements, you will see that this is a boring metal. Clean metal, no large Sommerfeld coefficients, and paramagnetic susceptibilities, and you might just discard the material as non-interesting. But the point is that if you keep looking at it, nature reveals its secrets to you. Okay, thank you.
Thank you, Mukesh. Yeah, we can have some questions now.
Thanks, Yogesh. Wonderful talk. I have two things to say.
Yeah.
One is that we were trying to do the same for the overdoped state of viscose.
Okay.
And actually we find numbers like 10, 11, 12.
Alpha?
Alpha.
Okay.
And till now I was like, this is wrong, it's not possible.
Okay.
But after seeing yours, maybe, maybe something is happening about which people don't know. I mean, maybe there are some very strong kinds of dissipations.
Right.
Because for cuprates, specifically the 1 or 2 experiments that have been done, show alpha like very clearly equal to 1, but we get an order of magnitude higher. That is one thing. And the second is, what about the plot of Hc as a function of t? Is it showing a positive curvature?
Yes.
Then you can just fit to the 2 band and...
Yes, we have done that. It's published already.
Oh, okay, fine. Yeah.
So I just want to comment that the cuprates are even funnier because I mean, you cross over different temperature scales where electron phonon should give way to electron and so on, and the slope does not change at all. So how this baton is being passed is amazing. Yeah.
And also for them, we need the quantum oscillation experiments to be able to calculate those.
Right.
But it's so difficult.
Right.
Okay, I go to
Professor Singh,
Yes.
thank you so much for this wonderful presentation.
Thank you.
I don't think I follow correctly that hidden magnetism is superconducting situation. Can you please elaborate?
Right. So, yes, this one. So the point is that in a Cooper pair, the total wave function must be antisymmetric because you have a pair of fermions. Now, in the normal S-wave superconductor, the 2 spins form a singlet, and therefore the spin part of the wave function is antisymmetric, and therefore the spatial part is allowed to be symmetric, and therefore S-wave can happen. Here the proposal is that because we have a multi-orbital system, the metals have d waves, d electrons, p electrons and so on. The electrons which are forming the pair are sitting on different orbitals at the same atomic site. Now because they are sitting on different orbitals, the orbital degree of freedom or the orbital part of the wave function also must be included. And this, because they are sitting at different orbitals, this is already antisymmetric. So the fermionic part, the antisymmetry has been taken care of by the orbital part already. This allows the spin and the spatial part to be symmetric. So because these, the two electrons are at the two different orbitals, the spin part can be triplet and still not break the violation of antisymmetry. So that is the state that we are proposing.
Yes, maybe last question.
Okay, so I think partly answered. So my question was like it's a electron phonon kind of superconductor, so PRS breaking.
Yes,
What
yes,
does
yes.
it mean?
Yes, yes, yes. That is what it means. So the spatial part can still be symmetric and therefore a full gap, but the spin part, which is symmetric, is triplet.
So thank you, Yogesh. I also have some questions. Maybe we can discuss in a tea
Sure,
time.
sure.
Yeah. So
Thank you.
thank you very much.